Let's talk about one of the important concepts in projectile motion, which is range. Range is how far the object travels in the horizontal direction. It's the displacement in the x direction. So what determines the range? How do we find delta x? Here's the equation for the x velocity. If we know Vx and delta t, we can find delta x. Vx is the horizontal velocity, which is always the same as the initial horizontal velocity. Delta t is the amount of time the object is in the air, which only depends on the y motion. We actually did this in the first example, but let's outline the steps for finding the range. First, we need to find the initial x and y velocities, the components of the initial velocity vector. For this example, the initial x velocity is 10 meters per second, and the initial y velocity is 19.6 meters per second. Second, we need to find the time in the air using the y motion. If the initial and final heights are different, like if the object is launched off a cliff, we need to use this equation to find the time. But if the initial and final heights are the same, like in this example, the trajectory is symmetric, so we know the final y velocity. Then we can use this equation for acceleration. The change in the y velocity is the final y velocity minus the initial y velocity. We can rearrange the equation so time is on the left, then plug in the values for the velocities and the acceleration, and we get 4 seconds. That's the duration of the motion, the amount of time the ball is in the air. Third, we use that time to find the range, delta x. The x velocity is the initial x velocity, 10 meters per second, and the time is 4 seconds. That gives us 40 meters for the range. Here's all 3 steps. It's always good to understand how to solve a problem like this, but we could combine these steps and come up with an equation for the range using any velocity and angle. We'll move through this quickly, so feel free to pause at any point. Also, see if you can derive this equation on your own based on these steps. We'll use this equation to find the time in the air. We replace the initial y velocity with the initial velocity times the sine of theta, and replace the acceleration with negative g. Then we rearrange things so we can use the quadratic formula. We can keep y initial and y final, or we can say y final is 0. We plug these coefficients into the quadratic formula, simplify that, and we get an equation for t, the time in the air. The range is the x velocity times the period of time. We replace the x velocity with the initial velocity times the cosine of theta, and we replace t with the equation we just found. So this is the range equation for any projectile motion. But if the initial and final heights are both 0, then we can simplify this a lot more. Y initial is 0, so the square root term simplifies to vi times the sine of theta. Then we can use this trig identity, 2 times cosine times sine equals the sine of 2 theta. Then we end up with this. This is the range equation you might see more often. Keep in mind that this only applies if the initial and final heights are equal, like if the object starts and ends at the ground. One more question that shows up a lot is this. What launch angle results in the longest range? So what value of theta will give us the maximum value of delta x? Here's the graph of this equation using 22 meters per second for the initial velocity. The angle, theta, is on the horizontal axis from 0 to 90 degrees, and the vertical axis is the range, delta x. No matter what the initial velocity is, an object launched from the ground will travel the farthest when it's launched at 45 degrees. If the angle is lower, the x velocity is faster, but the object spends less time in the air. If the angle is higher, The object spends more time in the air, but the x velocity is slower. Another important thing to know is that the range is the same at equal angles above and below 45 degrees. So the ball travels the same distance if it's launched at 30 degrees or 60 degrees, which are both 15 degrees away from 45. And the ball travels the same distance at 15 degrees and 75 degrees. But what if the object is launched from an initial height? Then the initial and final heights are not the same, so we use the general range equation, and the graph looks different. It's no longer a regular sine curve. More importantly, if the initial height is greater, the maximum value shifts to the left. If we keep the initial velocity of 22 meters per second, but the object starts at a height of 20 meters, the angle that gives us the maximum range is 36.6 degrees, which is less than 45. So that's a closer look at range in projectile motion.